Hi, everybody. Thanks for being here today. I mean, we have nice weather outside, and there is Pioneers Festival, there is Computer Vision Meetup, there is the Python Meetup, so I'm really glad you came today to also listen to my talk. My name is Christoph Körner. Today I will speak about ConvNetJS. Basically, I will speak a little bit about deep learning in the browser, so a little bit about what is deep learning and how can we do it in the browser, and does it make sense? And so we will discuss all these things. A little bit about me. Basically, I'm studying at the Technical University of Vienna, and I'm doing a lot with visualizations. So that's all for now. You will find the slides later in the internet, so you can look at all this information later. So, who of you is familiar with deep learning, or has at least tried a little bit? Okay, I see like 5 hands or so. Okay, so my idea was to give like a super brief introduction to deep learning, like 5 minutes or so. It's not much. Okay, it should be more like a teaser, an appetizer, so that later you can maybe go through the slides and click all the links that I provide to get more information. So you will definitely not learn how to do it, or maybe not understand it. Maybe every slide is a whole lecture on its own. So, but I will just want to give you the ideas so that you can understand like what we are doing in ConvNetJS later on. Since you're not super familiar, I maybe also skip the third part that took all my last weekend. But this might not be super interesting for you. But I have all the things prepared, so if you want to talk to me later, we can discuss this. So 5 minutes. Somebody takes the time, maybe. Okay. So what is actually deep learning, or what do we want to achieve? So it's basically we want to do some machine learning task, which is like a supervised learning task. So we want to learn something from data. In this particular case, for example, we want to do image classification. So we have some image data, and we want to predict which image class this is. We also saw the previous company, they're doing fraud detection. This can be also used for doing like, you analyze the mouse cursor movements, and you detect if this is a human or this is some bot or something like this. Based on data, this is all based on data. What can we also do with machine learning? Supervised machine learning, in this case, we can do localization, so we can find some parts in the image that we're interested in. We can make a detection, so we find the correct class and the correct position, and we can do semantic segmentation, for example, where we want to cut out certain parts that belong together. It's used in self-driving cars, in a lot of other technologies. In more general, what machine learning tries to do is to find is to do regression. So it's to find some function that matches your data, basically. So what you can see here is like in 2 dimensions, you have like the blue dots is some data points, and you want to find a function that approximates this data. This is just 2D. When we are in machine learning, the dimensions are much higher, so it's like more like 1,000 dimensions or like something like this. But the task is very similar. So you can look at this classification task also as some sort of regression. So you want to find a line, that separates some images from the other images. So you want to find this line. This tells you that these are cars and the others are airplanes or something else. So that's the goal, actually. So what do we need for neural networks in particular? So neural networks, we need first, we need these 4 ingredients. And as I said, like every one of these ingredients is like more than a lecture on its own. So, but you just need to understand like why do we need it and what we need it for and how does it work. You can look it up later maybe. So first we need a linear classification, then we need some nonlinearities to put together the functions to approximate the universal functions. Then we want to compute the loss, and then we do some optimization. But I will just go through this a little bit. So what we do is basically, I will talk about images now. So also ConvNetJS is focused a lot on images, but basically in the end, you're just working on numbers, on arrays of numbers, let's say. So you can have any data. So what you can see here is a very simple linear classifier. You take an input image, you put it in a column vector, just all the all the pixels, maybe to put first the red channel, then the green channel, then the blue channel. You just put it in one column vector. And then you have a very simple, like in 2 dimensions, a very simple line equation. So you have a weight. In this case, it's a matrix because we are in more than 2 dimensions. And we have a bias, and we compute some number. It's just a linear line equation. And we get some score. Yeah, and this score tells us something about the proper class. So actually, for each pixel, let's say, I need to have a weight, and then I can have a variable number of let's call it neurons, and this must correspond with the number of classes that I want to predict. The second thing that we need to do is if we have this very simple line equation, we want to combine these line equations to approximate any function. And we can only do this if we use nonlinearities. So we need to introduce some nonlinearity that either cuts a value if it's negative and outputs just the positive part, or here's a sigmoid function that just maps it to the range 0 and 1. So this is a little bit an overview of what we do. Here you see the input vector is the image. And you have this very simple linear model. You get some score. Then you apply a nonlinearity. In this case, it's a softmax function. Then you get another score. And then you want to know how good are you predicting the correct class, for example. So let's say you wanted to predict that the thing is a cat. So you have here a vector with the proper answer, which says 1 is a cat. So this is the correct answer. It says it's a cat, and it's not a dog, and it's not a cow, for example. So here's a 1, and the others are 0. So then you need a function that takes these two things and gives you, computes you the error. So it tells you how accurate is this prediction. So once you have the error, you can do some optimization. So the error is, as I said, computed by the class label and by this function. So this is the correct label. This is the line function. And it also takes some regularization loss. And this computes this error. And now we can optimize this error by finding the best weights. So this is a 2-dimensional weight matrix, let's say. And you want to find the values that are in the minimum. So you want to find the weights that best approximates your function. And so this was one of these dots. If you put a lot of these dots together, and if you put them in layers, you get a neural network. So that's a little bit how a neural network looks like and how it works internally.
Sorry? How
yes.
many layers you have in your network?
It depends. So you can start with just with one. Or you can go up to like 140 is something that I will show later, or even 250, or like the state of the art are, yeah, like about 200 to 250. It depends which layers you count. I will show this later. So these are simple neural networks. These exist for a long time. So what is new is the deep neural networks. So what is deep learning? You take all the things that we learned from neural networks, and you, instead of hidden layers, you do convolutions. I had some cool things today to show you what this is. So I have it on the slide, so I will show you later. You do convolutions, you do pooling, and you do many, many layers and many, many parameters. So these are actually like 4 ingredients: neural networks, convolutions, pooling, many layers, and much data is also a key ingredient. So what are convolutions? Convolutions are like similar to this linear function that I showed before, but is working only on a subset of the image, and you apply it patchwise over the whole image, and you move it over the whole image. And this is also applied to volumes. I've written it with volumes. So in this case, you're not putting your image in one column vector only, but you leave the image as it is. So it's like 256 times 256 times 3, the 3 color channels. And your filter, because they are volumes, they work on the whole channel. So they work on all the 3 color channels at once. So actually, they just add the filter response. And you do this, let's say, you do this once, then you get actually 1 layer of the output. But usually you don't do this once, but you do this 96 times. And then you get 96 layers, so you get the next volume. And then you do this again and again and again. Yeah, these are convolutions. And then there's a second layer. This is a pooling layer. What does it do? It's just reduce the dimensions of the volume by, for example, taking only the max value of here, of these 4 values, of these 4 values, of these 4 values, and its resulting is a volume that has the same depth, but in width and height is half dimension. And with these ingredients, you can build actually a deep neural network. I said many layers. So here you see somehow of the first architecture. You see here, actually, here is one, here's the input image. You see one convolution layer is in between this, going from this volume to this volume. Then there's a pooling layer, reducing the size of the volume. Here's a pooling. Then here's another convolution, another pooling, reducing the size, a convolution, 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 another pooling, and then you have the normal hidden layers, which are called fully connected layers here, the ones that you saw before. And I said many layers. Well, you can see these are already 1, 2, 3, 4, 5 if you only count the convolutions, and then you have 3 poolings or 4 poolings, and then you have some fully connected layers in the end, so you have a lot of layers. You have a lot of layers, so you might ask how many parameters do you have to optimize. I can quickly, let's show this. Which is this? This is AlexNet. So you have about, 25 million parameters that you want to optimize in this network. So that's a lot. If you take this as float values, you have 205 megabyte, just the parameters. So that's quite intense. How does this work here? Yes. So every year there's a new, there's a competition, and there's a new deep network that is released by all of the companies usually. That's one from Google. I think this is 2013 or 2014. I'm not sure actually. This is the GoogleNet. It is very deep. It has actually 143 layers if you count the single layers. But actually it has quite less because you see that there are some combinations here of layers that actually they're organized in a very nice way, and they help to reduce the number of parameters. The thing I forgot to say is actually why we have the convolutions instead of the fully connected layers, instead of the normal neural networks, is because they save a lot of, they have a lot of less parameters. So if you go back here, this is actually the pendant to the fully connected layer. This is just a filter with size 11 times 11 times 3. So you have 3 channels that you work on. So you have 11 times 3 parameters. And in the first layer, times 48. So this is the number of parameters. And if you go back to the fully connected layer, well, here you have 2048 times 2048. That's a lot. So what you will see actually that most of your network parameters are in the back there. So you try also to reduce these parameters. Interestingly, when you compute these things, actually most of the compute time is spent in the first layers because you have to move these little filters, let's say 11 times 11 pixels over the whole image, and that takes a lot of time to compute, compared to the other parts. And there's an even newer network. It's from 2015. It's Resonant from Microsoft. You can see these are just the conv layers. So there's nonlinear activation layers in between. There are pooling layers in between. So they're actually a lot more than they're drawn here. And there are some special skip connections over there that makes them super special and super deep. So what is ConvNetJS? As you can imagine, having such models requires some compute power. And usually these things only run in special software, and usually people use GPUs to run them. So setting these things up is quite tedious. Like installing Caffe, for example, and making it work to making it run on CUDA, for example. It takes some time to compile all these things and to make this work. And ConvNetJS actually is an implementation of convolutional neural networks for the browser. And it's quite cool, actually. It comes with a lot of things included. So it comes with a network class and some layers. So you have like the most popular layers. It comes with a training class. So you can make this optimization directly in the browser. It comes with some cool visual features. So you can visualize the activations and the weights and the gradients of the weights and so on. It does JSON import and export. And it has a lot of cool demos. And I will just dive in and show you some demos here. So here we're working on a handwritten recognition task. I will show you the data. Well, this is very weird. This is the database. We don't need this. Maybe you can see it here. Oh, I just run it here. Then we will see the data down there. Yeah, I will. It's running in the background, so the things are changing. I will show you at the top. Actually, it's a network. It's not very deep. It consists only of 2 single conv layers, 2 pool layers, and a softmax layer in the end. You see here the input image, which is a handwritten digit. And then you see the different layers, actually. So these are the different layers. And here you see the activations. So actually, these are the pixel values after sliding the filter. And you're sliding here 1, 2, 3, 4, 5, 6, 7, 8 filters per layer. So the depth is 8. You're sliding 8 filters per, so that's why you're seeing 8 pictures. And you can see every depth of the layer is doing something different with the input data. Some are edge detectors. Some are just detecting like the region of the number. And so every filter does something on his own. Then you see the pooling, that the values go, the images get smaller. And here, yeah, you can see, here actually you can see the result. So this thing is very good. So in a very short amount of time, it achieves like, I think, 80% accuracy. So here you can see this is the training data, the validation data. So you get an image inside, and it tells you like the probability of the class that it's predicting. So, but this is also, like this task is not very challenging. Let's look at another data set. Let's make this a little bit bigger. This is the CFAR10 data set. So you have a couple of images, and you have 10 classes. And you need to predict them accurately. There's another cool demo doing this. So let's do this. So you can fiddle around with all the parameters here. Actually, that's very cool to learn. This is a little bit bigger. I think has 1 conv layer more. But in general, it looks very similar to the previous network. This takes a bit longer to train that it converges. So actually, maybe I just load some pretrained network. This works here. Let me see. Yeah, not really. Okay, never mind. But you can see actually again that every filter is like has a different job. So you could understand that like the more filters you add, maybe the better it gets. And with the right architecture, actually this is like this. So you also need to like take care of how you organize your layers so that you don't get too small too early and you don't stay too big too long, so that you get some like good size throughout the network, where you can track your activation through the network and you can propagate your error back.
Question.
Yes.
During the training process, you are changing the parameters of the convolutions and the pooling, or
exactly.
And you change also the order of the filters and that kind of stuff, or just the parameters?
So actually, the only thing that has parameters is the conv layer. So this is this like linear function that I told you before that you move over the whole image, and the fully connected layer. These are the two things that have parameters.
Vary during the training process.
Exactly, and these are the parameters that you tune during the training. And actually pooling, you say it's a defined function. You say it's a max or average of a certain region. Like here we have a max pooling of, is called here stride 2 because you take a 2x2 filter and you move it for 2 pixels. So actually, but this has no parameters. So
the overall architecture of the network, is just like for experience. You say, okay, I'm gonna combine convolution.
Yeah, exactly. So there has been a lot of work and a lot of research how to come up with this architecture so that it makes sense. Like, how big do you have to make these filters? Like, how do you have to decrease them, and how you need to organize them so that the volumes decrease. So that, as I said, you don't want to decrease like too early, but you don't want because otherwise you are left maybe with 2 or 3 pixels, so you cannot detect a lot of things. But it needs to be like somehow matching, and that's actually also a challenge. And there are some different layers that have parameters actually, but I will not talk about this here now. So let's go back to this. So yeah, this is harder to train. Let's see the accuracy that we achieve. So yeah, you can see that it's not doing super good. I mean, this is not a bird obviously. So it has some troubles, but over time it will adapt the weights and it will learn to predict these values because it's actually it's learning to approximate functions, and that's what the task is in here.
Can you follow up?
Sure.
I'm just wondering, how do you define the filters, or is this what are the filters? Is that a standardized mathematical function?
Yeah. So the filters are like you saw this V actually in the beginning. So the filter is just a random matrix of values that is multiplied with like this y times v times x plus b. So you have the V matrix that are just random values, and the b, well, they are combined. Actually, just have a V matrix. And
you have to put weight into the what the filters do.
Exactly.
Random.
Exactly. Yeah. So actually, what you do is just a normal gradient descent. So you put random values in there. You compute how accurate your prediction is, and then you go back, propagate your error through the network, and you adapt the weights in each layer. And yeah, actually, it's a good comment. Like this, it's like computer vision brute forcing. So you just have enough training data to learn to approximate the function, and that's actually the key of machine learning at all. So if you have enough training data, you can approximate any function. Well, there is also some theory that proves this, that with hidden layers and non-linear activations, you can, in theory, also approximate any function. So, of course, there are some problems. I show you just one last cool thing. So on the website of Stanford, there is a pre-trained neural network with ConvNetJS running. Here you can see I don't know if you can see. You can see the layers. They are exported as JSON format. So you can see they're like, you cannot see. There are a couple of, I think there are a little bit more. There are like 17 layers, a couple of convolutional layers, a couple of pooling layers. And so let's make this bigger here. So you have the input image, and then you have I think these look like the ReLU activations. So you have the nonlinear activation functions output here. So you can see that everywhere in different filters, different regions of the filter get activated, and in the end you have like a white dot in the class where it's the most likely. Well, these filters are scaled so that they match in this nice grid, but they are not like this size. So there's a lot of stuff in the slides, so you can, if you're interested in this, you can just look at this. Yeah, so 2 cool things that I learned when I read the source code of ConvNetJS. One is typed arrays. I think I heard this before, but I have not yet used it. And then I made some tests and I found out it's quite cool, especially for this task where you have like very big arrays with like type numbers, like float numbers inside. So I adapted ConvNetJS a little bit. So I'm using now float 32 arrays, typed arrays. And like if you compare like the sizes of using a normal array and using a typed array with float 32 values is quite a speed up. So this is quite cool, but it's just because we are using like huge arrays. I think if you use small arrays, the speed up is not that visible. I think here in the test I used like arrays with a size like I don't know, like 1 million or something like this. So quite a lot. And the second thing is like how to write fast loops. So the fastest loop that I found is this one where you use length pre-caching and this pre-increment. Some of you might already know this, but for me, this was quite cool. So back to convolutions. So what are the problems, actually, of this thing? Well, first, all the things are computed in sequence. So there's no GPU, actually. You just run, you have for loops almost everywhere. ConvNetJS uses an array structure to have the layers. So you can only have a linear sequence of layers, which is bad. You cannot have weight sharing. You cannot have recurrent networks in ConvNetJS. The robot is implemented very poorly, but it's not a problem. You have limited memory. This is actually quite annoying. So if you load models with 200 megabytes or something like this, which I tried, I crashed the computer quite often on the weekend. Also, JSON is not an appropriate format to transport a lot of values, actually. Also, text is not a good format. But I'm not sure if there is a better format for transporting and loading binary data into the browser. Maybe images or something like this, but yeah. And training models in the browser, I mean, it takes a lot of time because you have these restrictions. It's really annoying. And usually what people do is they use pre-trained models. So there's a website, actually, there's a lot of websites that have pre-trained models that run them on a couple of GPUs, like for a long time. And then they save the weights and they export them. So what I did over the weekend is I wrote a little library that you can load these weights into the browser, and you can run like GoogleNet, for example, in the browser. So you can analyze the structure in the browser. And this is very cool because you can actually, without anything installed on your computer, just a browser, you can run a deep neural network, and you can use the tools that you're comfortable with. To debug the network. So you can jump right into somewhere, analyze the activations, analyze the forward pass, analyze the backward pass, analyze the gradients, and step through the network. And this is quite cool, actually. So I will stop here. I'll just show you like one run through GoogleNet, if it works. So actually, I'm drawing all the activations, so it takes some time. Maybe the light is not so. But you can see here, so this is a lot deeper. So this is the first convolutional layer. You can see already that their filters are doing like similar stuff, like detecting edges, detecting blobs, and so on. And you have activations here. Then you go smaller, and you have like a normalization layer, and you have like, you can visualize all the way through the deep net until the end of the prediction. Yeah, so it's quite deep. So I think this is quite cool for beginners to play around with these things because there's maybe a bug because the last layer looks like very weird. But it's very cool for beginners and for learning about deep learning. Okay, I'll just jump right to my very last slide. There are some more cool resources to learn about deep learning, about neural networks. I put them all in the slides. Feel free to go through them. You will find them in the comments of the meetup page. Thank you very much for your attention. I guess there are lots of questions. Maybe we have time to answer a few.
Well, I have one.
Yeah.
I think the example you showed with the, 10 categories of
Yeah.
features that you want to classify. If I saw that correctly, the training data was not that big, right? It was
Is
100 images. How do you avoid that it's not like totally overfitting if you have thousands of parameters?
So I think the training data from CIFAR 10 is like 6,000 images. If I'm not like we can see. Yeah, actually, definitely, you will be like running this in the browser. You will be overfitting, of course, to this little data that you have. I mean, there's no chance that you can train like, I don't know, like 10 million images of ImageNet in the browser. That will take very long. Yeah, so you have to live with this.
Yeah, so the browser variant is more for education.
Yeah, actually, yeah. The cool thing is actually first you don't need to install anything. If you have ever installed like TensorFlow or Caffe, you know that this is worth a lot. And the second thing is that you can just use the Chrome debugger, set the breakpoint in a forward pass in some layer that you're interested in, and stop there. Visualize the weights and just like debug the network. So it's really, really cool for learning and for getting started and to experiment, I think.
Yeah, but can you even understand the network as a person? I mean, isn't this the result of black box? Can you stop it and then make sense?
Yeah. Yes, you can. Yes. So, well, for example, you can visualize the weights and you can see, for example, if they make sense. So not the weights, but the activation. So you have your input image going through the network, and if one point in time your image activation is just black, you know that there is a mistake somewhere. And if you do like, I mean, usually you don't take like random weights, but you have some random initialization, for example. You have to be very careful also with random initialization, and you could do a lot of things wrong. So it's very, very nice actually to stop just in some point and see actually what arrives there and what continues from there.
Once trained, it should be actually fast enough to do actual work, or?
Yeah, actually, yes. So if it's not too deep, like the GoogleNet demo that I showed here, it was like 50 megabytes of weight, and the forward pass takes like 6 seconds. So this is not a good example. But if you train like with like 4 or 5 convolutional layers, what I would find very interesting, for example, I don't know if you have done something like this in the company already, to analyze the cursor data and make a real-time prediction if it's a fraud or not, or make a real-time classification of the type of user just by looking at the cursor speed and like how he moves the cursor on the website.
How many coffee?
But this could be quite fast actually. Yeah. But for I mean, the goal is the key point also to use convolutions for this is to make it the network actually the weights smaller to use less weights. So you could use ConvNets also there. Yeah.
I suppose it should be faster on Node.js.
Yes, I think so.
Can you basically use it for debugging and figuring out a good solution in the browser and then let it generate more data in Node?
That should work actually, but I'm not sure. Like it's definitely faster, but still, I mean, the limit is like using the CPU-only versions of Caffe, for example. You will not get faster than this, and then you will have to use some GPU implementation, and then you have to.
Probably make problems with RAM and stuff like that more than.
Yeah, it makes a lot of problems with this. Yeah. Actually, it would be very interesting to try this in Node.js. Yeah, that's true.
But it's bigger in WebGL, and then you can do the GPU.
Yeah, but WebGL is not super good for doing these computations. I mean, there's WebCL, I think, that enables this, but I had no time to look into this yet. But I mean, there's cool things coming. Once these things have access to the GPU, this will go into the browser, I'm sure. But if you have no access to the GPU, like computational access, then it's not very, very efficient in the browser.
Nice.
All right, thanks a lot.
Thank you for watching this talk. Down below you can find our channel ViennaJS, where you can find a lot of different videos about front-end and back-end JavaScript, and feel free to subscribe.